Hey everybody, it's Nick. I got a tutorial for you today that's about basically programming. We're going to be looking at the Arduino programming language, which is based on a language called processing. They're really similar, except the Arduino language is geared specifically towards controlling microcontrollers and things that are controlled by microcontrollers, basically turning voltage off and on. In like various ways. So to like turn on an LED, or to drive a motor, or to read a sensor, like like that kind of stuff. So a lot of what I'm going to be talking about, almost all of it, basically also pertains to processing, the programming language processing, and programming in general. What I'm going to do is try to compress a lot of programming ideas into a really brief tutorial that's going to help you guys use your turtle robots. Okay, so this is going to be pretty quick. I want to follow this up later with some more specific topics, and there's not going to be a lot of graphics today. You're not going to be able to see a lot, because what the code you have does is it activates the robot, right? And I don't have that capacity right now to actually show you what that output looks like. So I encourage you to make change. This is basically what I'm going to teach you with this video, is how to make changes with your code so you can experiment with your turtles. So I encourage you guys to follow along, make changes, let your turtle draw some things, and basically see what that feedback loop actually looks like. So first thing I want to do is talk about what the structure of code looks like in Arduino. And I've got a really kind of simple example here. If you look at all this code, it's kind of sort of confusing at first, but you have this, like, every piece of code, when you start a new program, you'll have setup and you'll have loop in this case. And it's actually pretty clear, like in this interface, you say put your setup code here, this runs once. This is kind of teeing up the ball so that you're ready to hit. And then loop is actually what runs, and in computers, right, it's actually running constantly. And this is how you get things to animate and things to move, is because the loop is running constantly. So again, it's kind of like, I don't know, like putting on your equipment and then kind of playing the game. Okay, there's your bad sports analogy for the day. So every program has that, but when you look at this code, it's like, wow, it gets really confusing. Well, here's your setup, right? And if you go all the way down, actually take that back. Yeah, here's your loop. Okay. This is the calibration code. This is what we use to basically figure out what our settings are for our robot, so that it can draw correctly, so that it goes back to the same points. You guys did this in class. Whenever you do your programming with any code I give you, make sure that you transfer those numbers that you found to that new code. Otherwise, it's not gonna draw properly. So you have setup, which runs once, and loop, which runs many times. Anything that's above setup is considered to be available to the whole program. These are like basically setting up some arrays that talk to the different pins on the Arduino, establishing angles for things like that. So just kind of setting it up. This is making the connection to the Arduino and setting the initial voltage. And then the loop is actually what tells the turtle to draw the square, and we'll talk about that later. Then there's other functions that the program has, and again, it's outside of the loop. This one finds the distance to something, and it's just a bit of math basically. But it takes that wheel diameter and the steps in the gear, and it can translate that to some kind of like a distance, so that when you say go forward 100. It actually knows what that means. Like what does 100 units look like in terms of driving this robot? And then you've got this other these other bits of code here. This is what backward does, what right does, and this is essentially turning the wheels, turning one wheel or turning another wheel a certain distance, right? And then these are the code that makes the pen go up and the pen go down. And that's what basically all the code that you guys are going to work with has in it. The only part that you're ever going to change is in this void loop. You don't have to mess with anything else. And here's our friends forward and left, pen up, pen down, etc. So that's what that looks like. Okay, so if you look at the very important thing is that the syntax for your code. So what you might call the sentence structure. Every statement is a line of code. Every statement must end with a semicolon. A statement does one thing. So in this case, you might say like set an integer to be 112, and we're going to call that wheelbase. So integer wheelbase equals 112. The big thing is the semicolon at the end of it. That means that you're done with that statement, and you can move on to the next statement of code. If you don't have the semicolon, if you're missing a semicolon, it's going to throw some kind of an error, and it'll probably give you a line number. Let's actually see if that works. I don't know. I'm going to get rid of that and then check my code. And then see, it already highlights it. It says, Nick, you forgot something in line 18. And there's a whole bunch of other errors, but basically, well, in line 17, right? Because it tried to combine these two things into one statement. You can't do that. So I'm going to go ahead and put that semicolon back. Now it's pretty happy. It's not going to crash at least. Yep. So there you go. Okay. So be very, very careful with that, especially when you're making changes to the code. Next thing we're looking at are functions. So function is some kind of like a command, and these are commands that most of the time exist. Like for example, setup is a function. Functions have left and right parentheses, and then inside of them they have what's called switches. And a switch is basically just a variable or something that basically tells that function like what to do. So the function that we're going to be really familiar with is going to be one like for example forward. Say go forward 100. So forward is like the command, left parentheses 100, right parentheses semicolon. So that's the function. And the function is like a command or like a tool. It's something that we're going to use over and over again. Some functions have variables and some don't. So loop, for example, does not. Pen down does not. These are just simple kinds of commands. Let's see here. You can make functions. For example, forward is a function that we wrote in the code. There's another function. Let's see, what was the other one they had? Like distance is a function as well. I don't need to worry about that too much, but just understand how they work. You have to call them. If it's a command that the system knows, like loop, for example, then it turns green. It might turn orange. It's just something that it like recognizes. Okay. In this case, these are commands that the system knows. They are functions that control the voltage for the Arduino. You don't need to worry about those too much right now. And actually, I should say too, if you're interested in what something does, you can go ahead and like double click it to highlight it, and then right click it, and you can say find in reference, and that will actually open up a window that explains what that is, which is what's really, really cool about Arduino and about processing. It's very easy to learn that way. Go back to Arduino here. Get my PDF back. Okay. Longer constructions of functions might use curly brackets. So you might say, well, Nick, this doesn't have a semicolon. Well, that's actually because the curly brackets start here, and then all of this stuff is actually attached to this function, and then it gets closed here, right? And in that case, you don't have a semicolon. What the statements inside of it have a semicolon. What does void mean? Every time you have a function that's like this, you have to say what it returns, like what the result is. And in void, it means nothing, right? Like a void is nothing. And in this case, when you run setup, it just runs this code. It doesn't actually output anything. It's just going to output nothing. And that's what it has to know. Okay, that's what that is. That's all that means. For example, in this instance, the like helper function step will return an integer. So it does all this stuff, and then it says return steps. So it runs this little bit of math, and then it's going to return the number of steps. That's all that is. Variables, you've seen a lot of these already in the code. So like wheeldam or wheelbase, you have the type, and then you have a name equals, and you set that to be some number. Sometimes it can be, if you're using characters or something like that, or strings, it could also be that. But in this case, we're going to say int x equals 10. So set an integer called x to be 10. In this case, int is a command, that means something is like an integer. That means it's a whole number, no fractions, no decimal points. Float is what you use when you want to have decimal points for more precision. Requires a little bit more memory, a little bit more math. That's why you actually tend to like declare things as an integer or as a float. You kind of let the computer know how much memory you're going to need ahead of time. If you're multiplying or dividing by numbers or fractions, you want to use float. Otherwise, it's going to drop some numbers, it's going to make things not calculate the way you want them to. A little bit of math here. Basically, if you divide something and you want an integer as a result, you're going to get a round number, right? So if I divide 4 by 3, it should actually be 1.33, but if you set it as an integer, the result's going to be 1. If you divide 3 by 4, in this case, it's going to round down to 0. You can't divide it with different types. So if I say that I want an integer, but then I put a decimal in, it's not gonna work. If I have an integer and I put in 2 decimals, it's not gonna work. And you can find that out experimentally. A float, you can mix things. You can say 4.0 divided by 3, and it will return 1.33. You can also say 4.0 divided by 3.0, and it will return 1.33. You could also just divide 4 by 3 as a float, and it will also return 1.33. So just make sure that you know what your types are. It probably won't affect you too much in this assignment, but it will affect you if you're getting the incorrect numbers back. So just bear that in mind. I would not make everything a float if you don't have to. Like, pay attention to the type that you're using. It's just a good habit anyway. A powerful thing about computing is that we can make a variable and we can make it a name for something. So in this case, I could just say x, but x might mean anything. If I say x position as the name of my variable, now that's a lot to type in. I get that. X underscore position. That means that you are saying, I'm going to look at something in the x-axis, for example. And that's pretty powerful. That tells another person using your code, which is really common, exactly what you mean. Okay? So this is a strategy to think about. By giving a number a name, you give it some meaning. So it's not just some random variable. It's the x-coordinate. It's easier to remember a name than a number, and it's easier to modify as you develop designs. So choose names that are descriptive, ones that are clear to people other than you. Can't remember how many times it's happened to me that I've written some code and then I've come back to it like a couple weeks later and I can't remember like what I was doing. I didn't put any comments in, or I didn't name my variables properly. You don't want to do that to yourself. You certainly don't want to do that to anybody that you're working with. So choose names that are, descriptive and that are meaningful and that are clear, and be consistent about how you use them. You can do things like have underscores in names if you need it. You can also capitalize letters if you want to. That's valid. You just have to make sure that you're using it the same way every time. It is cap sensitive. You cannot start a variable with a number. It will not work. That is not. You can say x position 1, x position 2, which is really messy, but you can. What you cannot do is say 1 x position or 2 x position. It will crash. It will tell you that's why it's going to crash. So just talking about, we talked about this before, that there's things that are inside of setup and outside of setup and outside of draw and inside of draw. This is important for something called variable scope, which basically means like where the variables are, or which things the variables are sort of like accessible to. Variables created outside of setup and draw are global. That means all of the code can access them. So if I write wheel diameter here and it lives outside of these functions, that means setup can use it. That means a loop can use it. That means any of these other functions can use it, and they do. That's a good thing because that's a variable that we want to be available. Sometimes though, you might have a variable like, let's say, x position, but you want to use it in different ways depending upon what function it's called. That's when you would put it inside the function, and you'd make a local variable. So if you had a variable that only exists, let's try to find an example of that. So for example, step, right? Only is you actually set it up inside this function. It's going to be returned by this function, but steps only lives inside of this function step. Okay, and that's because we only need it there. We don't need it anywhere else. And once again, you're trying to manage memory consumption. You're also trying to basically make it legible to the person using it. And if you only need it in one place, then don't try to clutter up the rest of your code. That's what that means. And the only reason I'm telling you this is because you may try to make a variable somewhere and it might behave strangely or it might not work, and it might be because of the scope of the variable. Okay. Next thing, big idea, is that math modifies relationships. Everything in our robots are using is represented by numbers, whether it's the pin or it's the amount of voltage or whether we're going a certain number of steps or a certain number of cycles. It means that we can change it or control it with mathematical operations, such as addition, subtraction. Math and numbers help us modify relationships. So we might be able to say, for example, we're looking at the distance that we want to go, and we're trying to convert that to a number that is in steps for the motor, right? And by making these like relationships in math, we can get the result that we want. So this is basically just like an algorithm, right? We can have a piece of code that says every time you go forward, you're gonna turn left, but then you're gonna add 10. And actually let's take a look at some of that stuff. For example, let me find that spiral code that we had. That's a really good example. So we've got a code to play with. Spiral does this because, right, the spiral increases each time. And so we can say, like, every time you go through the loop, we'll talk about this in a minute, you're going to multiply the length of the line that you're drawing by 1.02. That means that that's going to grow. So we've changed the relationship of that line every time through the loop. Big idea. To calculate, obviously addition and subtraction are a plus and a minus. Multiply is a little asterisk. And divide is a forward slash. Okay, that's how you use math. You do not divide by 0, it will crash your computer. It is impossible for computers to divide by 0. If you do it, you will get a divide by 0 error. You'll find out pretty quickly that that's not possible. That's just a quirk of computation that you have to learn how to live with. Also, sort of a corollary to this is not to write code that will produce a 0 if you have actually run like a division. That's hard to do, or it can be hard to do, but you'll find out when it happens. And what you can basically do is just make sure that the number is always like 0.01. You can add a little bit of fudge to it, but just don't get yourself into a situation where you can't divide by 0. This actually will happen in Grasshopper too. It's just computers won't do it. So anyway, if that happens to you, you need to find a way to prevent that from happening. That's the way to learn. You can also do little shortcuts because we love that in programming. So instead of writing something out like, say, x equals 1 and now x equals x plus 1, which we do this all the time. It's just basically called like an increment, right? You just want to add 1. If you wanted to do something like this really, really simply, you can also just do x plus plus. You guys have probably heard of the language C++. That's kind of a programmer joke. It's like the language C plus 1. It's like a better C or a newer C. C++. So anytime you see something that's just x plus plus or y plus plus or whatever, all that means is you're just going to add 1 to that. It's a very, very useful shortcut. You can also do minus minus, which is basically taking a variable and subtracting 1. You can also do a little bit. So that's only add 1 or subtract 1. If you wanted to add a different number, you can say plus equals, which is the same thing as adding that number. Yes, there's minus equals, and multiply equals, and divide equals, and those are all useful. And you can see here in this code, actually, I was really sneaky, and I'm saying multiply line length by 1.02, and now make that line length. And that's actually what's in that spiral code. Comments, you see a lot of these things, like you can do large areas of them. Anything that turns gray is something that the computer will not read, but humans do read. And that's extremely useful, right? You can leave a little bit of instructions. You can explain why you did something or what something is actually supposed to do. And that makes the code more human readable. That's a real goal. You should always comment things that you're doing. You can also leave notes for people to say, hey, don't change this. Or like, this is what you need to change. And that's what we've done here. // will do that. If you want to leave a long comment, you do a forward slash asterisk, and then when you're done with your Shakespeare, you can do asterisk forward slash, and that will stop the comment. And you can actually do, what's useful about this too is comments will turn off code. So if I wanted to stop a bunch of stuff, you can see it all turn gray there. I can just turn that piece off if I want to, just temporarily if I want to. Comments are extremely useful. Okay. Conditionals. So this is a really terrible diagram from XKCD. I don't know if you guys know 90s music, but it's a flowchart, right? So is it the 90s? If it's not, stop. If it is the 90s, stop, hammer time, or stop, collaborate, and listen, like Vanilla Ice. And the joke is basically, right, the conditionals they let us change the flow. So you can say, there's a test. Is it the 90s? If it is, you can do all this fun stuff. If it's not, you have to stop. And basically changing the flow of a program is really powerful. You can have a sensor that says, like, if we're about to go off a cliff, stop. The movie Speed, right? If the bus goes under 50 miles an hour, blow up the bus, right? So conditionals are extremely powerful. They're a way to make your programs intelligent, and they're a way to say you can run some code or don't run some code. A lot of conditionals are just based on numbers. So like in Speed, again, greater than or lesser than. So for example, if I say A is 15, and then I run a test and I can say A greater than 10? Yeah. Is A greater than 20? No, it's not. So these return true or false, and based on a true or false, you can have your program do something. Here's less than. Is A less than 200? Yes, it is. Is A less than 5? No, it is not. Very simple. You can also do equals. You can say, is A 15? Be very, very careful about this. Like, this means, is it equal to? This means, set this equal to. Okay? X equals 0 is a statement. X equals 0 is a question. Is X equal to 0? And as a true or false statement. A true or false statement, as you may remember, is a Boolean. That's what Grasshopper calls it. So we think about a Boolean response to something. You can also say, is something not equal? So equals is it something? Exclamation equals asks, is it not that number? So if A is 15, you can say, is A not 5? That's true. Is A not 15? No, it is 15. It's false. What you can do, here we go. Now I let the cat out of the bag here. It's just a speed reference here. So you can use a test as a statement. So I can say if, and then I can put a test in. If that test is true, run whatever happens inside of the brackets. If the bus is less than 50, if that is true, then blow up the bus. Go watch Speed. You'll know what I'm talking about. Yes, so if the test is true, if runs whatever statement. If the test is false, it skips the statements in the brackets, which is also useful. There you go. So you can say, for example, let's set a variable, and then we run a test. If it's less than 5, then move the robot forward 100. What about this test? If I say A equals 15, and I can say, is A greater than 40? No, it is not, right? So nothing should happen. Be careful of the brackets. You got to make sure that's enclosed within it, or it's not going to work properly. So conditionals control flow is another strategy. Pay attention. These are things to kind of bookmark to say, because these are the big ideas. When we talk about big ideas of computation and big ideas of programming, these are things that pertain to anything that we make that's computational. Anything, especially that uses something that's involving programming or processes. So a conditional is a test that returns either true or false. It must do that. The outcome of the test can decide whether or not a program executes a statement. This is the flow of a program. Use conditionals to set rules and constraints in your programs. That's actually another useful thing too, right? So the constraint would be to say, like, hey, the CNC won't be able to work outside of this area. So if you go outside this area, then you need to stop the bit. Okay. So this is, this statement would actually run, right? Because 15 is actually greater than 5. This is all in here. Oops. I'll turn off my Wi-Fi here. I don't need that. Okay. Let's see here. So I think I just repeated myself. Wow, I totally have extras. Okay, so that's all. You've already seen that. There's also a statement called else, because you could say, well, Nick, what if I have a test, but what if I wanted to do something if it is false? So the first part of it is, if this is true, run this code. Else, which means otherwise, do this. So if A is greater than 5, go forward. Otherwise, go backward. Make sure you look at where the brackets are. The program will try to help you with that, but you got to be really careful about that. You've got to have those curly brackets open and close. And you can do all kinds of loops. You can say if this and then another if inside of it, or if else if. You can do really, really complicated logic with your conditional statements. You can only use else if it's inside of an if statement. If the if statement is false, then the program runs whatever's inside of else. Okay, that gets us to loops. Like once we have variables and once we can test, we can use loops. Loops are some of the most powerful things that we have. They're the power tools of computation. They give us the powers of repetition and iteration. This is what makes computers really fast. They can do things that are really difficult for humans, because they can execute things accurately and quickly, repeatedly, like this jackhammer, right? Computers excel at repetition. By repeating small changes, simple iterative rules can create complex forms. That's really powerful. You can use for loops to simplify repetitive operations. There's another kind of loop called a while loop, which I will talk about later, but a for loop is going to be the most straightforward for us right now. So I'm only going to talk about a for loop. A for loop structure is compact, and therefore easier to manage and edit. The spiral uses a for loop. You can see this for. We're going to talk about that. So here's a simple loop for a circle. So actually, if you look at going all the way back to our Arduino code, the calibration code, actually that even has a loop in it. It has lots of loops in it. So we can say for, and this says when x equals 0, as long as x is less than 12, increment x by 1. And then it just says basically go forward 100, go left 90 degrees, and then go back through the loop. That's what that loop is doing. If you change that code, so this says start at 0, go to 12. So that says loop at 12 times. That's 3 squares, right? Because we're going to go around. Takes 4 moves to make a square. Forward, left, forward, left, forward, left, forward, left. The circle is a little bit different. It says start with 1, go to 468. Well, 468 for most of our robots is the number of ticks in a revolution of the wheel. That's what that number is for. So 468 times, 467 times, because you start at 1. Go forward 1, then turn left 1. And so a lot of really tiny moves. So that's the difference between, 4 big moves and 400 some odd little moves, right? You go from a square to something resembling a circle. And if we change that, we get the spiral, right? So we're going to move 15 degrees, a little bit more than 1, obviously, but less than 90. And every time we go through this loop, so we go loop from 1 to 50, basically, 1 to 49. We don't actually get to 50. We're going to increase the length of the line by 1.02, which is going to gradually increase that. So we start small and we're going to spiral outwards. And so basically by changing the increment of it, we can actually grow this thing. So there's 3 examples of loops right there, going from the square loop to a circle to a spiral. And I'll kind of break it down a little bit for you. But so every time you have a for loop, it's actually like 3 statements, but we just kind of compress them. The first statement always makes a variable. So what are you going to test? What are you going to observe to make sure that the loop should be running or not running? And then you have a test. In this case, it's just, is I still less than 468? Right? And then iterate. So you basically say add 1 to I. So what this sets up is a loop that's going to run 467 times. That's all that this does. There's all kinds of ways you can set a variable, different names, different amounts. You can set it up as a variable in the rest of the program. You obviously have different tests you can run. Is something equal to something? Is it less than something? Is it greater than something? Different ways you can iterate. You can just add 1. You can subtract 1. You can multiply, etc. And then as long as that loop is valid, as long as that test is working, run whatever is in the code, this stuff, and then when you're done with that, go back through the loop again and then run this again. And that's how for loops work. And a loop will execute itself until it's done, and then the code will actually move on, for the most part. So here's like a loop for a square. I wrote these really large, variable names, but I wanted to be very clear. So the number of iterations is 0. Set the number of iterations to be less than 4. So we say 0, 1, 2, 3. That's 4 times. We're going to increment it. Go forward the square size. This is actually a variable that I can set that will let me change the size of the square. So that's really useful. So somewhere else in my code, I would have a variable called my square size. That's a very easy way to tell the user, hey, if you change this variable, you change the size of the square. Right? This I don't need to worry about for my user, because that doesn't need to change. It's still a 90-degree turn. Here's a spiral. So just what I showed you here. So we have our spiral. It starts in the middle, and it's going to go 49 times, and the length of the line is gradually going to change, and every time it moves forward, it moves 15 degrees. You can change all these different parameters. I mean, if I want to make a different spiral, but this generally works. And somewhere, yeah. So basically, this would just live in your loop. Okay. So there's the basic looping pattern. You can say this is the start, this is the finish, and this is the spacing. If you change this number, you change how many times it's actually going to go through that loop. What you don't want to do is have an infinite loop, and you guys have probably heard of this before, but basically it's a loop that cannot stop. That will crash your computer. It will run out of memory, or it just won't be able to finish. It's not a good thing. In this particular instance, I have created a loop here, a for loop, that will, so in this case, I take x as 0, I subtract 1, I go forward, and I say as long as x is less than 10. Well, x is always less than 10. This is a loop that will never stop. So you've got to create conditions that prevent infinite loops. And so here's a strategy. An infinite loop is a loop that cannot terminate. This locks up the robot. Do not create conditional tests that cannot be false. Okay? As soon as the test is false, right, the loop stops. So you want a test that will eventually be false. Be careful not to create tests which under certain conditions may never be false. Sometimes you just have to learn this. You'll actually find this out by breaking it. It won't hurt the robot. Trust me. Randomness. Randomness is something we love as architects because it's something that like we have some control over, but we don't have absolute control over, and that's really interesting to us as designers sometimes. It's very easy to do in Arduino, and I use this a lot in the random walk program. The random walk just says, you can read this code now, right? We're looking at 200 iterations, basically 199. Again, you never quite get to. Remember, it doesn't say equals 200. It says as long as it's less than 200, which means when it equals that, it will actually have stopped. So I have a function within a function here. I say go left, a random number between negative 45 and 45, and then I say go forward, a random number between 5 and 10. So note the brackets here, or the left and right parentheses. I've got to enclose that properly or it's not going to work. So random is a function that you put in a low number and a high number, and it returns a random number between low number and up to but not including high number. And random will return a float unless you specify otherwise. Okay, so that's really key to understand too. It will return fractions. There you go. So if I say like roll a die from 1 to 6, well, it's actually going to return between 1 and 5 and 99999. Same thing here, negative 11 to 1.3, it will return everything up to negative 1.2999. It never gets all the way to that number. So just if you want a number in that range, you actually have to go above that range. So like one thing to avoid is using randomness randomly. We talk about this a lot in programming, garbage in, garbage out. If you're just generating, something kind of thoughtlessly, it's not going to necessarily result in a beautiful design. You still have to think about the principles of order, balance, contrast. It's a way to manufacture complexity, but you have to think about like what's the range of numbers you're using, what are you doing with the numbers, that sort of thing. You're controlling the randomness. Like you're specifying the range and the tests and everything like that. You're not out of control. You're the one in charge. So thoughtful design is really key, especially when you're using randomness. Okay? That's something that you'll get better at as you go, but I want to kind of call that out. So this is the random walk, and the random walk, like I said, is just you're going to run it, 199 cycles. It rotates within a 90-degree kind of cone, which is what I thought was more interesting. But I tried different tests when I wrote this, and that seemed to be the most interesting pattern. And then it moves forward randomly, and my thing is wrong. It's actually between 5 and 10 steps. I found that if it didn't move at least 5, it didn't produce much. Like a lot of the time, it just looked like it was doing something, but then it didn't actually produce a drawing. And so you have to give it a pretty good distance. And this is kind of what I mean going back here. I had to design the randomness so that I would get an interesting form of random walk. Okay, so that's something to take into consideration. When you start to apply, there's a special kind of looping that computers can do called recursion. And you see this a lot like in fractal patterns and things that happen in nature. So things that are self-similar. So this is like broccolini, I think it is. I can't remember. But it's this vegetable, or it's this plant. And you can see that like it looks like a spiral, but then within it are these little spirals. So they're all the same kind of pattern being repeated. And that's like really fascinating. It's a way that nature packages a lot or packs a lot of information into a space. So that it doesn't need a lot of information to make a complex form. It's really fascinating. So its self-similarity is a formal principle of nature as well as computing. You can reuse code within code to create more complex structures. So what does that mean? I have this program that I gave you guys. I think it's called Recursion, if I'm not mistaken. Yeah, Recursion. Go ahead and open that up. And this code is a really common kind of fractal piece. And so I write a function called tree, and then the function has 3 variables, right? And it's the number of iterations. So how many like cycles does it run? How long is the branch, and what's the angle between branches? And you'll find out by playing with this, and I really encourage you to, that you can get all kinds of effects by playing with these numbers here. The more iterations you have, it's going to dramatically increase the amount of time that it takes to make a drawing, so be careful with that. You need a long enough branch length also, because otherwise, you can see here that every iteration we divide the branch length by 1.5. And so if you don't start with a large enough branch length, it's going to be a very, very tiny tree. It's not going to look like anything. And then the angle, which is interesting. A 30-degree angle looks very tree-like. A 90-degree angle is really interesting. I encourage you to try that. I encourage you to experiment with that. It's more, I don't know what you want to call it, more Frank Lloyd Wright-y. It looks more like a motif than an actual kind of natural thing, which is very interesting. So how does this work? Well, again, you got to kind of run it to really see it. But so we just say it's a simple sort of thing where I say, if you're at iteration 0, quit the program. That's what that means. So just like return, just get out of that tree. And then the rest of the code says go forward the length, turn, and then run tree. And change the variables that you run the tree with based upon what iteration you're on. And that's what's interesting, is that so you can see that I've written this program called tree, but then the tree program is actually using that program inside of itself. So it has to finish this program before it can finish the greater program. That's the recursion. You've got a program buried in a program. It's like a turducken of code or something. And when you see the robot, doing this, I think you can kind of understand it better than if you just run the code like in processing, because you can see the robot going all the way out to the end of the tree and then closing each of these tree loops before it can actually finish and get back to iteration 0. It's really interesting. So each time you go through the loop, it subtracts 1 from iteration until it gets to 0. It divides the branch length that it has by 1.5, right? The branch length which is inside of this program, and it keeps using the same angle. The angle actually doesn't change. But it goes out, it goes left, and it draws, and then it goes, turns right a couple of times, it draws something, turns left, and then goes backwards. So it actually returns to the same point that it started, and the code remembers that initial, or at least it kind of seems to know. It's basically just parsing it, backwards. But you'll see it move out, and then it moves back. And then it draws again, and then it moves back. And it keeps drawing backwards until it gets to the end of the branch. And it's really interesting. And you can see, and I should have used this image. So like I said, so it actually starts out out here, and then it goes back and draws. It goes back to here. It'll go out and draw again, go back. And that's a Y, so it has to finish, this Y has to finish, this is a Y, this is a Y, that's a Y, that's a Y. That's the recursion, that's the tree structure. And this is 3 iterations, right? 1, 2, 3. Well, actually, maybe it's more than that. I apologize. It's probably, well, anyway, this you can find out experimentally, but you can see that it has the similarity, right? This Y. Well, if you change that angle, you'll get something different. You can make it a much tighter tree, or you can have it spread out more. But it's this branching, it's gonna be like symmetrical. And there's other ways of those are styles of recursion that you can look at, like L systems and things like that, and actual fractals. But this is a really nice demonstration of that idea. And the cool thing about it that I like is that it's basically like 10 or 12 lines of code. but it's really compact, right? Okay, so give that a try. Like, those are the different pieces of code that I gave you that you can experiment with, and they all demonstrate these ideas. You've got code for conditionals. You've got this, you've got the random walk, recursion, the circle, variables, etc., etc. And this is going to be, a good way to get started. I want you to go ahead and play with these things, experiment with them, break them, bring your questions to class. We'll make some cool stuff with your robots. All right, have a good one. Bye.